All right, we can officially start. So, hello everyone. Welcome to our fourth edition of the Quantum Machine Learning Conference. My name is Paweł Gora. I'm the founder and CEO of the Quantum AI Foundation, which is a non-profit organization established in Poland, aiming to support research, education, collaboration in new technologies. And we also closely collaborate with QWORD and its local QCAS and QPoland to build the open global ecosystem for quantum technology. So just this is in short. You can find more information on our website, and the links will be provided at the end. But today and now I will give an introductory talk for this mini conference. So it will be an introduction to quantum machine learning. As you probably know, because there's also information on our website, there will be four talks today, or actually there will be three talks and one workshop. So first I will give an introduction to the conference and the quantum machine learning. Then Karol Bartkiewicz from Poznań will tell about machine learning and optimal quantum information. And then Grzegorz Czelusta from Jagiellonian University in Kraków will tell us about detecting clouds in multispectral satellite images using quantum kernel support vector machines. And finally, there will be a workshop given by Sebastian Zając about variation quantum algorithms. Okay, so let's start with the first talk, with the introduction to quantum machine learning. So as you can see, this meeting is recorded. So if there are some questions, please post your questions on our chat, and hopefully we'll have some time at the end after each talk during the Q&A session to answer the questions. So at least in my case, maybe in case of other talks, the lectures will be more interactive. But as for now, let's just try to post our questions on the chat. Based on the registration, I realized that we have some participants who have good background in physics, but not necessarily in machine learning. There are also some participants who have some background in machine learning, but not necessarily in quantum computing. Might be also some participants with some experience with quantum machine learning as well. So it's not easy to, or it was not easy to decide what would be the optimal scope of this introductory talk. So I decided to first give a brief introduction to machine learning in general, and then brief introduction to quantum computing, and then an introduction to quantum machine learning. And later in the next talks, our next speakers will provide more information, of course. So regarding machine learning and artificial intelligence, which is a more broader domain, so in general, the intelligence can be considered as an ability to acquire and apply some knowledge and skills through learning, reasoning, planning, or problem solving. So these are just examples of some tasks or skills indicating that we deal with an intelligence. So the artificial intelligence in the intelligence demonstrated by machines. Machine learning is giving computers or machines the ability to learn from data without being explicitly programmed. So the machines can just learn to perform such tasks, and it is considered to be a subset of artificial intelligence or subfield of artificial intelligence. And contemporary deep learning is an area of machine learning that is considered as the most promising, or at least we can observe the biggest progress in machine learning, specifically in the field of deep learning. But I know that during the talks today, there will be also information about some other machine learning algorithms and machine learning approaches. So it's good to know that in general, there are several types or several types of tasks in machine learning. So we can deal with supervised learning, in which the goal is to infer a function from labeled training data to learn some concepts. And here we have some examples like linear regression, decision trees, random forests, and so on. We may have unsupervised learning, in which we don't have labeled examples, and the goal is to discover hidden structure from unlabeled data. And k-means or self-supervised learning are just examples of the unsupervised learning approach. We may also have the reinforcement learning, in which some agents are learned by interaction with the environment. So in given states, they perform some actions and get a reward indicating how good the action was. And there might be also semi-supervised learning, which is a combination of supervised and unsupervised approach. So only a portion of data is labeled. So in all these approaches, currently the most successful model or approach is based on neural networks. So neural networks are also inspired by how the real neurons in our nervous system of people work. And so we have an activation function that takes some inputs, potentially transformed by the weights, and then these inputs are combined and transformed to produce the output that can be an input to another artificial neuron. And here we just have some examples of popular activation functions like sigmoid or ReLU, and you can check more in different sources. But of course, in neural networks, we have multiple or many neurons. So for many years, it was difficult to build and train neural networks with multiple hidden layers, but currently it is state of the art in many approaches, so that we have many layers of neurons connected with each other, and there might be also some recurrent connections with previous layers as well. It's good to know that deep learning is a broader area than just deep neural networks. In general, in deep learning, we learn data representation, and deep neural networks are not the only representation of deep learning, but recently proved to be very successful in many applications. So in other machine learning algorithms, usually the engineers are responsible for finding and defining features. So this is called feature engineering. But the ability of deep learning to just learn the features and representation of the features from data is one of the reasons why it became so successful. So it's good to know about the general approach to train or learn neural networks, because there might be, or there will be many such information in the next talks as well. So in general, in training the neural networks, the goal is to minimize some kind of loss function like mean squared error or cross entropy by modifying the weights of connections between neurons. And there might be also many approaches to do it, but currently one of the most successful and frequently used approaches based on the process that is called the backpropagation, which is based on the gradient descent. So basically, we compute the gradients of the cost function, so the derivatives of the cost function over all the weights that we have, and then we modify the weights in order to, or in the direction corresponding to the best improvement of the cost function. And this training can be performed in batches of the training set. So we may take many examples, many samples from the training set to perform the gradient descent. There might be a stochastic gradient descent in which we randomly select elements from the training set to the batch. There are some approaches to improve the standard gradient descent, like including gradient from the previous iterations, or there might be also some more complex optimizers like Hermes-Prop or ADAM. We may apply some kind of regularization or dropout techniques to prevent overfitting and to enhance generalization to unseen examples. But in general, the problem of finding the optimal configuration of hyperparameters like the values of the learning rate or dropout is also an interesting area of research in which quantum computing can be potentially applied as well, because as you will see, solving optimization problem or combinatorial optimization problem is one of the areas in which quantum computing can be potentially applied. It's good to know about some popular machine learning applications like playing games, speech to text transformation or automatic translation, object detection, or natural language processing and answering questions using some chats. All right, so now about quantum computing. So what is the quantum computing and how is it different from classical computing? So the simple words, quantum computing is just computing um, in which the computations are governed by the laws of quantum mechanics. So in classical computers, we have bits and classical gates. In quantum computers, we have qubits and quantum gates. So now what is the difference? So in case of classical gates, I believe that you know that the data are represented is using zeros and ones, and this can be inputs to the classical gates like AND or not and so on. So I believe that you heard about the classical gates. But in case of quantum computing, even the representation of information can be different, because instead of bits, which mathematically are relatively simple, so they can be represented using elements from the set 0, 1. So qubits, in case of qubits, the state may be in a superposition of states 0 and 1. So mathematically, it can be a unitary vector of the two-dimensional Hilbert space over complex numbers. So even this mathematical representation seems to be complex. I would try to explain it in a simpler way, hopefully. And one of the consequences and the differences is that in case of classical computers, the state is determined. So we can know exactly whether the state is 0 and 1, and the state can be changed from 0 to 1 and vice versa. But in case of quantum computers, to get values 0 and 1, we can do a measurement which breaks superposition, right? And then we just have a probability of getting 0 or 1, which depends on the qubits of the state of our superposition. And the quantum gates can modify the qubits and modify the probability of getting 0 or 1 after the measurement. So this is a standard representation of a qubit and this quantum superposition. So we have this basis state 0 and 1, which can be considered as an orthonormal base of our quantum system in this two-dimensional Hilbert space. So we can think about these states as vectors as well. And A and B are complex numbers, right? So, and it cannot be arbitrary complex numbers because the squares of their amplitudes are probabilities of getting 0 or 1 in a measurement, so that the sum of the squares should be equal to 1. And it turns out that multiplying these complex numbers A and B by a unitary vector, so a vector of the length 1, doesn't change the quantum state, because only the relative phase between the coefficients of two basis vectors has any physical significance. So the phase of the quantum system is not directly measurable. So that's why A and B can be transformed to spherical coordinates, and we can also think about the states of qubits as points on a sphere that is called a Bloch sphere. So in this sphere, this basis state 0 and 1 can correspond to antipodic points, and other superpositions can correspond to some other points on this sphere. And sometimes the quantum computing with a single qubit is also called a journey on a Bloch sphere, because actually, as we'll see, the quantum gates can just modify these points on the sphere. So they correspond to rotations around some axis, as we will see. And these are just some notable examples, well-known examples of quantum gates, like Hadamard's gate, X Pauli or Y Pauli gates. Some gates parameterized, so that I believe that there will be many information about such gates during the talk today, during the other talks today. But there might be also gates operating on more than one qubit, like the CNOT gate, in which one qubit is a controller for the NOT gate. So for this X Pauli gate, which is some kind of quantum negation on the second qubit. And it's good to know that any quantum circuit can be simulated to an arbitrary degree of accuracy using a combination of CNOT gates and single qubit rotations. And it's also good to know that these quantum gates, so first of all, as I said, they correspond to rotations around some axis on our Bloch sphere. So this is an example of a rotation for the Hadamard's gate. They also correspond to some linear operations, unitary operations, actually, in our two-dimensional or Hilbert space. In this case, two-dimensional, because we operate only on a single qubit. In general, when we have n qubits, we'll be in the 2 to the power of n dimensional Hilbert space. And so that's why we can also describe these operations, unitary operations, using unitary matrices, or we can also describe the operations, but just saying how these basis vectors will be transformed in our space. So this is the notation for the Hilbert gate, for the Hadamard's gate. And as you can see, it transformed these basis states into superposition of the basis states, so that the probability of getting 0 or 1 after the measurement is the same in theory. X Pauli gate, as I said, is a quantum negation, because 0 is turned to 1 and 1 to 0. And you can see the matrix of this operation, and it represents a rotation of pi about the axis x. So that's why this is called x Pauli gate, and there are also y and z Pauli gates corresponding to rotations around y and z axis respectively. And these rotations can be also parameterized, and this is frequently used in quantum machine learning. So this is an important example. It's also good to know what are the matrices for rotations around some number of degrees around the y-axis in this case. And this is a matrix, this time four-dimensional matrix for the CNOT gate operating on two qubits, in which one qubit is a controller, triggering the NOT operation for the second qubit. And the true power of quantum computing comes with quantum parallelism, in which we can operate on multiple qubits at the same time, because initially we can prepare a state that is a superposition of all possible 2 to the power of n states, 2 to the power of n numbers. And then we can just apply some quantum circuit, so different combinations of quantum gates to all these quantum states at the same time, and modify the probabilities of obtaining the states after the measurements. So this is an example of a quantum circuit. So here we have 8 qubits. In case of, so initially they were in the state 0, the basis state 0. In case of 3 qubits, there was no quantum gate applied, so the result of the measurement is 0 always. Here for qubit 6, we have this x Pauli gate, so it's negation. So we'll get 1 with probability 1. And here we have the Hadamard's gate. So we'll introduce non-determinism in our measurement, and we have 3 CNOT gates. So this qubit 4 becomes a controller for qubit 0, 1, and 2. And finally, when we do a measurement, it turns out that in about 50% of the cases, here for qubit 4 we'll get 0, and then the values of qubits 0, 1, and 2 will be 1 always. And in another 50% of the cases, the result here will be 1, and the values for 0, 1, and 2 will be 0. So that the results, so there will be 2 possible results corresponding in this case to ASCII code representation of my initials. So this is just an example of relatively simple quantum circuit that you can also build by yourself, for example, using IBM Quantum Experience for your initials as an exercise. So just to summarize why this quantum parallelism is important as well. So in case of classical computers, on n bits, we can process only one n-bit number at the same time. In case of quantum computers, using n qubits, we can process all 2 to the power of n-bit numbers at the same time. Another difference is that in classical computers, the results are deterministic. So randomness is in fact a pseudo-randomness. We have generators of pseudo numbers. But in quantum computers, we may have the randomness that is let's say real randomness. So what is this real randomness in the world is also a kind of open question, because there are different interpretations of a quantum mechanics, but we can think that this is the randomness that we can get thanks to the quantum mechanics. It's important to see that there is a stable progress in development of quantum computers. There are many different approaches and many different technologies to build quantum computers, like ion traps, superconducting qubits, photonics, or neutral atoms. It's good to see that we observe a stable progress. So there are companies working on quantum computers and announcing from time to time that they built a larger quantum computer with more qubits, better quantum volume, and better fault tolerance or fidelity of qubits. So we can observe that there is a progress, and as for now, it's hard to say how this area will evolve, but for sure it's interesting to observe this progress. But it's also good to know that contemporary quantum computers are still noisy. So we live in the so-called NISQ, noisy intermediate scale quantum area. And we are not advanced enough to reach fault tolerance and to profit sustainability for quantum supremacy. And that's why even in quantum machine learning, we also have to design algorithms that should take this noise in account if we want to run some experiments nowadays. Some applications of quantum computing, I believe you may be aware of them. So quantum cryptography or breaking some classical cryptography algorithms, solving combinatorial optimization problems that frequently occur in finance, transport, logistics, but also machine learning and artificial intelligence, sampling from difficult distributions, which may also find applications in machine learning, but also to generate art, simulating quantum processing to discover some new materials or drugs. And finally, it's good to say about this quantum machine learning. So this is an image based on the presentation given by Maria Schultz. So she classified the algorithms in 4 groups. So there might be classical machine learning algorithms operating on classical data. There might be classical algorithms operating on quantum data or in quantum environment. There might be quantum algorithms operating on classical data and quantum algorithms operating on quantum data. So in general, it is expected that this area, so quantum algorithms operating on quantum data might be most promising probably, but we'll see. The future will show us what will be the outcome. So an example of applying quantum algorithms to classical data are variation quantum algorithms. So they share a common structure where a task is encoded into a parameterized cost function that is called ansatz. So it's a parameterized quantum circuit that is evaluated using quantum computer, and then a classical optimizer trains the parameters of these algorithms and of these ansatz. So it's emerged as a leading strategy to obtain quantum advantage for these NISQ devices. And Sebastian Zając will tell much more about variation quantum algorithms in his workshop in the last session. But just to give you some intuitions here, so we have this ansatz. This is a parameterized circuit preparing the quantum state. These architectures can be generic and problem agnostic, but there might be also problem specific. So here is a typical architecture of the ansatz. So they correspond to a unitary operator, parameterized, that can be expressed as a product of several unitary operators, parameterized using just a single parameter acting on an input state. And these unitary operators can in turn be decomposed into a sequence of parameterized and unparameterized gates, as here in this example. What are the requirements of the cost functions computed using the ansatz? So its minimum should correspond to the solution of our optimization problem, because this approach can be especially useful applied for optimization problems. It's useful to have the cost function that is operationally meaningful, so that smaller cost values indicate a better solution quality. It should be possible to efficiently estimate it by performing measurements on a quantum computer. So an implicit assumption here is that the cost should should not be efficiently computable with a classical computer, so that we should expect some quantum advantage. And this cost function should be trainable, which means that it should be possible to efficiently optimize the parameters. And it's important to know that, in fact, this is a hybrid algorithm, right? So there is a quantum subroutine. So given a set of parameters, it returns a set of measurements, but the rest is done classically. So given a set of measurements, we can classically calculate the energy value. So it's usually some kind of averaging. It performs the optimization procedure. It calculates what a new set of parameters should be, checks whether we have reached the minimum, and so on. And these are just examples of some classical optimization procedures that are used in this case. And usually choosing a right optimization method is for a given problem is crucial to just ensure the efficiency of VQE algorithms. And why these algorithms are good now in the NISQ era in which we have these noisy devices? Because in these devices, there is a lot of noise. So every time we apply a quantum gate, there's a substantial chance that we'll apply a different gate. And this is just one of many flavors of noise that we can get. The qubits don't live for too long. So after some time, we can be pretty confident that the information is lost. So the number of operations that we perform is limited. So we don't have too many qubits. And there might be some restrictions on which qubits can interact with each other. So as a consequence, we can use only a small number of operations per qubit. The number of qubits is small, and we cannot assume that everything will go according to plan and there will be no errors, right? But even if there are errors, we should still get a reasonable result, or we should expect to achieve reasonable results, to ensure the robustness. So why VQE are good for this area? So VQE are pretty flexible when it comes to the circuit depth. So we can initially use a simple and relatively small ansatz and then build a deeper circuit. So this approach is called layered VQE. And VQE have been shown to be somewhat resistant, so robust to noise. So even in the presence of noise, it can give the correct results. So some people even claim that a pinch of noise might help with the optimization process because it helps to escape local minima. And here we can see some notable examples of VQA algorithms, QAOA, and its variants, and variation quantum eigensolver and its variants as well. It's good to know about quantum neural networks in which some classical nodes are applied together with quantum nodes, which are also variational circuits. And it's important to ensure that this variational circuit should be also differentiable. So we should be able to calculate the gradients over the parameters of this variational circuit. And there might be some hybrid approaches in which hybrid neural network can be combined with QAOA or some other VQA algorithms. And this is an example of this work. It's a master thesis of Justyna Zawadzka, one of the members of QPoland. Finally, there are also some kernel methods, which are based on mapping input data into a higher dimensional feature space using kernel function. So kernel function is a nonlinear transformation, transforming data to nonlinear computations. And of course, there are very popular classical kernels in machine learning applied, for example, in support vector machines, but there might be also quantum kernels. And I know that Grzegorz Czelusta in one of his talks will tell you more about quantum support vector machines as well. And finally, there might be approaches in which we have quantum data, but we apply classical algorithms. And there are just some examples to quantum state tomography. So it is a process by which a quantum state is reconstructed using measurements on an ensemble of identical quantum states. We have quantum feedback control and quantum circuits optimization. And if you are interested in such applications, there is a very good paper about modern applications of machine learning in quantum sciences. And there is also another interesting paper that is a totally different approach. So as you might know, in quantum computing, we often use something that is called a QUBO formulation, which is in fact a representation of our optimization problem as a polynomial of many binary variables of the degree at most 2. And very often we just reduce our optimization problem to problem of solving such kind of optimization. In this case, we often use something that's called a relaxation parameter, which just matches our objective function that we want to minimize with some additional, with an additional part corresponding to satisfiability of some constraints. All right, and this coefficient regulates the quality of the results and the probability of obtaining correct results for quantum computing. So it is important to set the value of such a parameter correctly and optimally, but it's not an easy task. And recently there are such works like the QROS approach in which machine learning can be applied to train or to learn what should be a good value of the relaxation parameter for a given problem instance. So in this paper, it was applied to the traveling salesman problem. So it's good to know that there are many approaches to how to enhance machine learning, and I have already found and read about almost all quantum counterparts or hybrid counterparts of classical algorithms. Some people claim that we can already achieve some advantage, but I think it's not probable at this moment. But it's good to know about some notable applications of quantum machine learning for Earth observation, and Grzegorz will tell you more about this approach today. I know that QML is also applied for neuroimaging, for Alzheimer's prediction. So for sure, we know that quantum enhanced machine learning can achieve some good results in learning tasks. But whether it can outperform classical machine learning, it's hard to say, perhaps, but it's probably still too early to at least validate it and even prove it. And for sure, it would be difficult to prove as many other things in machine learning, but also for sure, it's an interesting research area. So that's why it is also one of the reasons why we organize this conference. So when we should expect the quantum advantage, or in fact, should we really consider quantum advantage in case of quantum machine learning? So actually, there's a paper from Maria Schultz and Nathan Killoran in which they claim that, in fact, we shouldn't now talk about quantum advantage because this is really too early. But in fact, we should rather just think about long-term research agenda will focus on understanding how quantum computing and machine learning can be combined, rather than focusing on whether or not one beats the other. But it's also good to know that 2 years ago, there was a paper published by researchers from Google claiming that they find potential quantum advantage in machine learning. So they demonstrated exponential advantage in quantum machine learning, which means classical devices with unlimited computational resources could not achieve the same results in the same time. And this study showed that quantum machines could learn from exponentially fewer experiments than the number required for conventional experiments. But to be honest, I'm not sure if this approach has been validated and really proved. I know that there are some disputes, but this is another interesting paper that was published just yesterday. So I found it yesterday evening about, in principle, super polynomial quantum advantage for approximating combinatorial optimization problems via computational learning theory. So there was also another paper published 2 years ago claiming that we can already expect at least polynomial time advantage for QAOA and maybe also some other variation quantum algorithms. So as you can see, it's an open research area. There are many interesting papers, and for sure it's a good area for research. And at the end, I would like to tell you about uh, some existing libraries for coding quantum machine learning programs. So it's good to start from PenElane, which was the first library for quantum machine learning. So initially it was considered and even called and advertised as a TensorFlow of quantum computing until Google released its TensorFlow Quantum, which is also a library of an extension of the TensorFlow. And finally, there's also a Qiskit machine learning module in Qiskit as well. So if you are interested to learn more, so first of all, I invite you to stay with us for the other talks at this mini conference, but it's also good to know that there are also some other good resources available on the internet. That's all for my side. Sorry for a slight delay. We also start a few minutes later. If there are some questions, please post your questions on our chat and I will be happy to answer. But now I would like to give the Zoom to our next speaker, to Carol, who is already with us. So Carol, first of all, I will enable the screen sharing. And if you are ready, you can already start sharing your screen.
Okay.
So in the meanwhile, I will try to reply to the questions that we have on the chat. So Carol, currently I can see the main slide, but I can also see
Yes.
probably the next slide. I'm not sure if it's the intention.
This is not intentional. This is because I have two monitors and I have to switch to the right one. Okay, let me do this again. Okay, it should be correct. Okay, this should be fine. Okay, so thank you, Pavel, for this very nice introduction to quantum machine learning. I think this will make my talk maybe shorter, so maybe we can actually recover some time. Okay, so I'm actually working in this field for some years now with some, let's say, short breaks because I've been working on organizing a new study program at Adams University related to quantum information processing and programming. But essentially, I started working on this topic seriously in 2019. So already I know the many details, and I got to know some very gifted people who work on this. And together with my collaborators from Poznań, Czech Republic, and from Riken from Japan, also Franco works in the US at Michigan. So we were able to obtain very interesting results on this. Okay, so you see that essentially because quantum machine learning was not that popular some time ago, we started collaborating with just like people all around the world that we just wanted to exchange some ideas. We are physicists. So for us, we had to learn some computer science and the theory on machine learning. Fortunately, it's linear algebra and mathematics is all the same. So it's quite natural to go there if you are a quantum physicist, okay? So just to show you like a timeline of how we think about quantum machine learning from a physicist perspective, this is the inception of quantum physics, and somewhere around 2013, maybe 2009, people started to like seriously thinking about applying quantum computers to learning. Okay, so basically, quantum computers allow you to speed up linear algebra. It's why not to use them to like just transfer naively some ideas from machine learning to quantum reality. Okay, so this was the original idea. So people tried to just solve some small computational problems with quantum computers, and to show that in principle you can have asymptotic speed up. So in Poland, we had a long history of working on quantum information theory. So one of the first papers was actually on this was written by Professor Ingarden in 75. So we already work on this for almost 50 years here. So this is so our quantum information theory environment is quite well established. Okay, so other motivation was like applications. Okay, already Pavel told us that there are many types of learning and applications, but if you think about like just the impact on business and just other areas of our everyday life, it's incredible. Okay, so you have to deal with ads. So it's estimated that about 35% of Amazon's revenue is due to like recommender systems that the machine learned. Okay, so there's a lot of more. And this slide is overloaded intentionally because it's just to show that like you can continue and continue, and there are 3 dots, and so this ellipsis just show you that there are many problems, okay? And there are also challenges that stem from classical machine learning, and probably we can do something about them in quantum realm or not, or maybe some problems just become irrelevant. Okay, but one problem that is apparently very attractive to address it's energy consumption. It seems that even if you use a quantum computer, the computations consume very low energy in comparison to classical system that has to perform this computation. So this is if there will be not like a real quantum advantage in terms of speed up in computations, we can always like justify buying a quantum computer for some data center just to like lower energy consumption for some for using this device as a coprocessor for something. Okay, so there are many players. I know some people from these companies. Actually, I also last month I spoke with a person who works at Google Quantum AI, and they're still hiring. So currently at those problems related to quantum computing and quantum machine learning. So the groups are as Google and IBM are growing. So recently, so I think that for quantum computing, IBM hires like about 800 people or more, and Google is hiring about 200 people and more. They're still hiring now, but so this is so they are like expanding. Okay, some companies do better, some companies do worse, but definitely if you look at this, what's going on in the world, they are very interested in pushing this these ideas forward. Okay, so already you've seen this typology for quantum machine learning. So we actually started investigating this from this perspective. So you want to have some systematic approach because it's very easy to like confuse many things if you don't do this properly. Okay, so you typically want to think about this like data processing is done classically, or this is done, or is it done by a quantum computer to some extent, or is data generating devices quantum or classical? Okay, because this is actually quite interesting way of thinking about this. It allows you to choose the best technique and maybe to explore some new ideas, to generate new ideas, what to actually analyze if you think about this scenario. Okay, so I will give you in my talk some examples of these problems that we actually addressed experimentally or theoretically in our research. Okay, so some very easy problems to understand are related to classifications and clustering, so I will talk about them. And I will talk about quantum kernels. There are obviously also quantum artificial neural networks, but for practical reasons, they are not very often used because of the noise. So if you want to compute highly let's say, you need to, basically you need a deep quantum circuit usually to implement some interesting artificial neural networks. And this leads to accumulation of noise if you have no error correction, and it is now we don't have it. It doesn't help to use this, and probably it's better to think about some quantum kernel. Okay, so we actually wrote our first paper on this in 2018 on quantum kernels, and before that there were some papers by Schultz and Kiloran, for example. So they wrote a paper on using support virtual machines. So on quantum kernels for some applications. There was also a paper by this IBM group in 2019, and they invented very let's say clever problem to actually show that it's better to use a quantum computer for this type of classification. And usually when people try to invent some problem to show that some advantage, they think about let's say some graphs. So it's good to know some graph theory also. So if you cannot cut some graph it's not like separable by one cut of a problem. So you need to many cuts. Then it's probably better to use quantum computer, and then you could expect some advantage. So this is some way in which the engineers at those large companies, they think about like creating problems to demonstrate that they are making some progress, so the investors don't get anxious. Okay, but this is so what is this kernel method, and why do people are interested in this? Okay, so basically this is something that was widely used in the 90s because of like we at that time we didn't have much computing power, but the memory was quite abundant. So we could just maybe use to solve some machine learning problems. We could maybe afford working in larger space, but we couldn't do many computational steps because of it was very expensive. So in our case, like in at this stage of quantum devices that we have, it's similar because Hilbert space grows exponentially. If you add 1 qubit, it just grows twice its size. So we have large space, and complex computations are expensive because we have many errors and we cannot correct them without having thousands of qubits and high fidelity gates. So still we are closer to this situation we were some time ago, but it still will take a few years to get there. Okay, so basically the idea is that instead of like trying this to find this boundary in two-dimensional, let's say, space where it's obviously non-linear, we want to find a linear boundary. So we just go to a larger space where we expect that this boundary will be linear. Or speaking about this differently, we just want to find a function that will transform these coordinates in a way that they are linearly separable. Okay, so this is basically something. So first we want to map these coordinates to some function. So this is like feature mapping. This is one of the steps for applying kernel method, and the other is just to find the coefficients for this for f function. Okay, I just realized that I don't have a pointer. Okay, here. Okay, you should be able to see this better now. Okay, so so you want to have this f star function, and this is these parameters. Once you know the kernel values, are easy to find by just linear programming. So this is easy to solve. Okay, so the tricky part is now to get these kernel values, and if these are multi-dimensional. It's like a multi-dimensional vector. It's easier to just measure this kernel value instead preparing quantum state properly and then measuring this kernel value than just computing it on a classical computer. So if there is some justification for using this method if this kernel is hard to compute classically, but this is not the main motivation. The motivation that is, let's say, more rational, because now computers are rather fast, is actually that maybe we can construct feature maps that in quantum systems that are easy, that are easy for quantum systems to implement in a natural way and hard to compute or to obtain with classical computers. Okay. Okay. So this is the problem that we usually want to solve. So there are some labeled examples. So this is supervised learning. We want to find these coefficients and we want to measure these kappa values. So the thing that we have to remember is that okay, so we have a choice of this function. So Pavel showed that there are like polynomial kernels, there are Gaussian kernels, other kernels. So what's easy to implement on a quantum computer if you use Hilbert spaces is to prepare this sort of like cosine kernel squared. So basically, this is something that it should be a superposition of quantum states. And then this should be overlapped. So if you prepare this state, you measure its probability of it collapsing to this state, and this corresponds to kernel value. Okay, and it seems that if you take this, if you look at this approach, if you have a longer look, you realize that there are many ways of expressing this kernel. One way, it's like if you just think about like okay, so this is just like some sort of polynomial, okay? So maybe I can do this way. This is not the best approach, but this was used in literature before. So this is something that you can find in literature. It's easy to explain, but it's easy to use fewer qubits to get the same result. You just use different coefficients, and the number of qubits just drops exponentially. So it's very important to like think about all those details when you're creating your quantum algorithms. So you should think about, okay, I don't have unlimited number of qubits, so it's better to maybe use fewer qubits, but with smarter this feature mapping. Okay, so this is one of the aspects. And you can choose these parameters are in many ways. So we analyzed actually many natural phenomena that are associated with scattering light and other things that lead to this sort of states. And it turns out that you can actually optimize, for example, this the variance for this kernel. I mean, the kernel should be like very tight, so you could basically use like a wider or a thinner pen for selecting your boundaries. This is something that you could actually think about like graphically if you want to visualize what's happening. Okay, so if you use like few qubits and you want to have like very a narrow kernel, so you want to have this optimal line. Okay, so this is what you do in theory, but finally you have to construct some setup. So either you use superconducting qubits as for example in IBM quantum experience, or you can just build a quantum setup with photons and some wave plates and beam dividers and photon detectors. So this is what we do in a laboratory in Czech Republic, for example. And then you encode quantum information in, for example, in polarization of single photons. So this is like horizontal polarization here, and also in this dual rail encoding. So you can use top or bottom line just to know where your photon is. And to some extent you can prepare the states that are required. So we can actually use this to get some nice power cosine kernel here, and this is what you would expect. Okay, so you just run some support vector machine in Python, some ready library for this. I think we should use this as scikit-learn for scikit-learn for support vector kernel. And you can use actually custom kernels here. So if you don't, you can just write this kernel here, or you can use experimental data. And this is what we did. So we prepared some points and we just use it as a kernel that we optimized. Okay, so this is for experiment. So first you choose like some hyperparameter to find the best kernel. Okay, it seems that this one is better. And then in experiment, we try to repeat that and to see how well our experiment fits theory. Okay, it seems that we reached some better result here in case of this theoretical case, and this is because just at some point was because of some errors here was classified correctly by random not because of this was not optimal kernel. Okay, so sometimes noise helps a bit, but this is in this case this is just like artifact of small sample. Okay, so you can extend this idea of using optical elements to build larger bulk setups, and you could have more complicated optical interferometers, and basically you can stack them not only horizontally but also vertically. So people are building more larger and larger, more complicated setups for machine learning. Okay, and so what is actually some expected speed up in terms of let's say just pure theory. So if you think about so everything boils down to a problem of state preparation. If you are able to prepare this feature map of arbitrary state to arbitrary state fast in optimal way, this is so you can obtain some speed up. This is a result of Grover and Rudolph from 2002. So basically there is some 1 over log speed up in comparison to this let's say classical approach when you would like to compute something. Okay, so because classical power kernel, if you want to compute it, this is the computational complexity, and this is the complexity of quantum kernel. Okay, you just have to run one experiment if you can actually meet the criteria of Grover and Rudolph for state preparation. It's not always possible because sometimes the state is so complicated, or maybe in a different language, its parameters do not fulfill all the important conditions for this to work. So then you don't have this speed up, but sometimes this is possible. Okay, and but what it's actually important, I already mentioned, is that we want to find quantum advantage in expressive power for the kernels. Okay, so you want to find some interesting kernels. This is the holy grail, and some kernels that allow you to maybe solve some problems better, not only faster. Okay. This is some interesting picture. This is from the University of Science and Technology in China. This is no longer the best, let's say, optical computer for the purpose of machine learning. So, but you can already find some press releases that claim that we reach this supremacy over classical computing. So some, I think Science China news portal claim that, okay, you can actually reach 180 million times faster computing than in comparison to the world's most powerful supercomputers. So I tried to research, okay, what do they mean? And actually They try. They mean some specific operation that is related to random tree search. Okay, so it seems that just by running light through some uh, specific configuration of this setup, you can reach some of the speed up. But usually people don't forget about this, that you need time to like adjust this and everything like that, and think that this will kill any type of speed up. Okay, so this is, but this, nevertheless, it's very encouraging. Okay, but let's go to some like examples that are easy to understand. Okay, so what's actually happening if you take like if you want to compute a distance in quantum space? So there are many ways of defining a distance, and one of the easiest way to like measure and like to use to an experiment is to compute Hilbert-Schmidt distance. Okay. Usually people think about like overlap, just they use something that is called a swap test, but this is only usable for pure states. So if you want to use like also coherence of states of diagonal elements of the density matrix to encode information, it's better to use this Hilbert-Schmidt distance, okay? And then you can use it to, for example, implement K-means clustering algorithm, okay? Because every time for every iteration, you compute distances from, for example, centroids, and so then it's very important to compute this efficiently. Obviously, classical computers can do this fast, but still there is some speed up to be expected, okay? Because actually what you need to compute for computing this distance are just like 3 measurable elements, okay? So if you have a right optical setup, you encoded state rho 1, for example, in spatial encoding, so we just like dual rail encoding, and the other state in polarization encoding, this rho 2, you can just use a positive valued operator, positive operator valued measures to just find these quantities, okay? I will not go into details how these experiments work because this is just a short talk, but you can find it in our paper. But what's interesting is like this large scale experiment, because this is just for like 2 qubits. So this is the space of parameters is rather small. Okay, we have like 15 parameters, and this is not enough to do something very challenging. So the complexity for this, so the number of parameters, basically of Hilbert-Schmidt measurement in this approach grows like logarithm of n. So this is the number of parameters you have. And the complexity of classical distance computation is like polynomial of n. Okay, so definitely it's something that could reduce the complexity and not only complexity, but also could lead to some lower energy consumption for in some applications. And also you have this quadratic enhancements in capacity of this approach in comparison to just using a swap test, because you can use coherence to encode additional parameters. Okay, so this is one of the results. This is how well it actually fits theory. So this dashed line is actually experimental result, and the solid line is vertical one. So it's good, but it's not perfect. Still, if you use it for clustering, this is the This is actually we wanted to estimate some fraction of misassigned let's say points in comparison to like perfect distance computation, and this is how it looks with this distance for our two means, okay, in distance in units of variance. So it's not bad, it still could be useful, okay? And we also apply different types of learning to in our research. So we used reinforcement learning because it's related also very interesting computational problem like boson sampling, but it seems that we can do this efficiently using classical approach. So, but nevertheless, if you have a quantum setup, you don't want to simulate it classically because it's very complex thing. So it's usually it's better to just measure some quantities, use classical control algorithms, and then to improve your setup. But this is potentially computationally hard to do, to have a perfect simulation of the setup. So we prefer like using with real quantum device. We use real quantum register. We make measurements. Everything is imperfect, and we just use classical control to improve this setup. And it seems that this is a very useful approach for experiments, because it allows you to let's say, set this device to work in optimal way without having full information about all the sources of errors and some problems in your network. Okay, obviously this has to be done. If you know the optimal solution, then you can do this. But if you don't know it, then you don't know if your procedure works perfectly. So we apply this for some known problems like finding optimal cloners. Okay. So this is what we did. We also wrote several papers on like what the deep learning can actually do, what people struggle with in quantum physics and non-quantum information processing, like finding some better criteria for separability of quantum states, or diagnosing some problems with quantum routers and so on, or maybe even with for planning quantum networks, where you have to like quantum find connections between two nodes. Okay, this is not trivial using using classical algorithms like Dijkstra algorithm or some A-star algorithms. This will be still very very difficult, because of the properties of how this of the errors. Okay, so sometimes they can compensate each other, sometimes they don't compensate, sometimes they don't. They actually make things more difficult. Okay. So so we can think about this. Okay, so distance is not always additive in quantum networks. So this is why some algorithms have to be, let's say, replaced with other classical algorithms. Okay, but speaking about networks, so this is like the last, I think, important case, just to give you some idea of how classical machine learning is different from quantum machine learning. Okay, so if you consider something that is called generative adversarial network, so it's an idea used for training, let's say, two networks that they're adversarial. One is to generate something, and one is called generator. And the other is to tell, okay, if the input that it's receiving is from this generator, or this is like a real sample. Okay, so this is like a real photo of something, let's say of a cat. This is like a animal that is used for every machine learning, I think, experiment. And this is, let's say, generator that is trying to generate fake images of a cat. Okay, and then you just feed this with let's say, if you want to train generator, you have to like feed it with something, random numbers and samples, and you train it to just to deceive the discriminator. Okay, and real samples are used to train the discriminator for, and also they are used to train the generator. Okay, because you cannot like do this. Okay, in a different way. So this is just like standard backpropagation you use for standard networks, but you use we train the networks in rounds. So once you train discriminator, then you train generator, and so on. And finally, if you reach some equilibrium between these two, so this cannot cheat this one better, and this cannot discriminate better between these two, you are now done with the training. Okay, and the question is, can we avoid just training in rounds? Okay, because this is like, this seems to be very unstable. You have to choose various parameters, and it seems that this is possible, because if your discriminator and generator are described by reversible unitary operations on large Hilbert space, they actually this is just like circuits that evaluated the like the performance for for generating discriminator. So if you have something here, you prepare like a real sample with this circuit R, or you generate a sample for with generator G lambda, and then it's fed to discriminator, and the discriminator is then like used to compute the overlap between input and output. If it's like 1, this means that each time this means that it works perfectly. The same goes here. So, and we call this like the synergic approach, because you can then like, it turns out that you can just use all of this at the same time, even and everything is like reversible. And this works more or less like an autoencoder. Okay, so you can think about this. Like we find some parameters that allow you to encode some information here, and then there's additional just quantum bit to flip this value. So this always so if this because in perfect case, the discriminator cannot decide like, okay, if generator is perfectly trained, it should give the same output as for real samples. So this is the reason for this controlled NOT gate. Okay, so you can implement this in like using deep circuits or shallow circuits just by using this swap test version. So this allows you to make shallower circuit, but at the expense of having this controlled swap gates, which is for multi-qubit states. This is a nightmare to implement, so it's not always the best way to go. Okay, but finally, your cost function that you actually work on is something that is composed of real and this real sample and generator overlap. So this is something okay. You compare your device and real samples, classical distribution of parameters for your samples, and also about this is the performance of discriminator. So this is something that is a product of these two. Okay, and this is this function is then minimized. And we have to somehow implement this. If you want to implement arbitrary unitary, this problem just becomes very complicated. But if you know what to expect, you can use better circuit ansatz, for example, as here in this Nature paper. But we use this general ansatz for our purposes, just to be sure that we can find the right circuit in our simulations. So we performed some experiments using this IBM quantum computers, and we plotted some figures of merit like fidelity or just cost functions. And it seems that if we just minimize this cost function, also this fidelity between generator and real samples grows to almost 1. And this probability of discriminating signal properly also grows to 1, but this is like 1 minus this, so we don't have overlap over all these lines. So this is just like random initial condition. Probably this is just a lucky choice, but you can use different configurations, which is what we did also for other states for numerical simulation. And this works quite well. And in comparison with this standard adversarial approach, it also performs not bad. Okay. So before we used the Nether-Mead approach to optimization, because you don't want to use gradients for machine learning on noisy devices usually, because if you have a noisy gradient, then you just perform some, uncontrolled random walk. And if you want to not have random gradient, you want to reduce the noise, it will be very expensive to estimate it properly. Okay, so this is what we usually use gradient-free optimization methods. And this turns out to, we tried different optimization methods for machine learning usually, but for the devices that we use that have quite considerable noise, gradient methods just do not work. Okay, they can just take a long time to converge. And if you use, for example, the Mead method, it's guaranteed that even with random perturbations, it will eventually reach at some point the optimal solution. Okay, so what are the conclusions? So we can actually still do some interesting observations and on many levels, not only from like computational complexity or machine learning, but also if you consider like just how to encode information. There are many ways of doing this in quantum devices, and this is something that we are trying to do in our group, to invent some ways of encoding information in the best way possible, and also to pack the information in the quantum system in optimal way, because it seems that many problems like this kernel problems, if you try to use kernel methods on a quantum device, strongly depend on how the information is encoded, okay, and how the kernel is actually implemented. So there are some clever approaches to this using Qiskit already developed by IBM with some ready circuit ansatz to like make this easier, so you don't have to use arbitrary circuits. But you have some class of circuits that have some connectivity, okay, that is that's required to have like, let's say qubits talking to each other. But sort of technical effects, so technical problems are basically solved like this by companies who build their own devices. But what we do, we just look for some enhancements that can be like achieved with slightly unorthodox approach, and also to find okay, this is on the screen, to find some new paradigms for learning, or maybe just to show that some situations are not equivalent in classical and quantum realm. Okay, so I think I talked for too long, but just to show you that this is, I think that was the last slide, but yes, this is the last slide. So just to show you that still in physics, just using learning, machine learning, or classical or quantum is a good idea. Is we can compare artificial neural network and the results obtained by the best people in the field for some classification problems. Okay, if this state is entangled or not, you have two copies, some local measurements and some overlap measurement here. Okay, so is the state entangled or not? So theorists say that there are some criteria. You have to perform 12, let's say, measurements, and you can have success rate like this. Type 2 error, this means that you don't classify entangled states correctly. And type 1 is you just mislabel separable state as entangled state. And if you just allow like small, minuscule amount of type 1 error, you just go above the best theoretical results by a huge amount, okay? So this is something that people cannot do easily because it's too complicated, but for a computer, this is not a problem. And you reach huge let's say, improvement, okay? Because you need fewer measurements and you basically outperform, let's say, the best criteria out there by a lot, okay? Okay, so this is it. So this is, I think that I just give you like a complete overview of how this looks like from a physicist perspective, and I hope that I get you curious about the next talks. Okay, thank you so much, and
Thanks.
that's it.
Thank you, Carol. Thanks. So again, if there are some questions to Carol, please post your questions on our chat. And Carol, if you can stay with us, you can try to respond to the questions, because now we have to move to our third speaker, Grzegorz Czelusta. And maybe I'm not sure when exactly Sebastian will finish his fourth talk, but maybe if we have time, we can also try to ask some questions still in person if the other speakers will stay with us. So we'll see depending on the time and availability. But now it's time for Grzegorz. I'm not sure if Grzegorz is with us now.
Yes, I'm here.
Yes. Okay, great.
Okay, so
We can hear you. Thank you. Thanks, Carol, once again. All right.
Okay. Can you see my screen?
Yes, we can see it. At least I can see it.
Okay. Okay, so thank you. Good morning, everybody, once again. Today I'm going to talk about cloud detection in multispectral satellite images using quantum kernel support vector machines. This talk is based on article that we under the same title that we wrote it as a part of project co-funded by the European Space Agency. And so first, let me explain some concepts that appear in this title. First of all, what are multispectral satellite images? Let us imagine that we have an image. Usually, it is an RGB image, so it consists of three images taken in three different colors: red, blue, green. And multispectral images are taken in many different wavelengths of light, for example, in some infrared spectrum and so on. And for example, as an example, in my talk, I would like to focus on images from the Landsat 8 satellite. It is an American Earth observation satellite. And we use data from this satellite to train and test our model. Here we can see different bands in which Landsat 8 photographs the surface of Earth. So these are these multispectral images in this 9 different wavelengths of light. And here, for example, we can see two pictures of the same area, but taken in different spectra of light. First image is taken in spectral bands 2, 3, and 4. So 2, 3, and 4, so blue, green, and red. And the second one is taken in bands 3, 5, and 7. So 3, 5, and 7. These are green, near infrared, and shortwave infrared. And satellite images play an increasingly important role in many aspects of human activity. Applications range from cartography, meteorology, ecology, and so on, to security and urban monitoring. And as a result, tens of terabytes of raw imagery are generated daily by satellite constellations. And this large volume of images, which are captured, makes them difficult to transfer, store, and analyze. So the task to reducing the size by extracting useful information is a critical issue in real world applications. And on the one hand, we want to remove cloud regions from pictures for further processing. And the other hand, also the efficient detection of cloud cover on the Earth's surface is important for meteorological and climate research. So our task is to recognize clouds on this type of pictures. And in our experiments, we focus on these 4 bands, so red, blue, green, and infrared. So in our case, each pixel in the image is represented by a vector of 4 numbers, intensities of these 4 bands. and we want to label these pixels as a cloud or no, not a cloud. Okay, so back to the title. Another thing that needs to be explained is the term support vector machines, or SVM for short, which was explained in the previous talk, but let me explain this again. So in binary classification, we assign one of two labels, let's say -1 and 1, to each data point in a set based on its features. So if we think of the data in terms of points occupying feature space, the problem can be thought as partitioning that feature space so that each of its two parts contains only one class of data points. So let's say we have some points representing different values of pixels, and we want to split them into two categories. Of course, this line is not good splitting, but this line looks quite good. But also, this line also looks quite good. So there is the question, which line is better? And suppose we add a new point here. We see that it should rather be in the blue class, but according to this splitting, it is in the green class. So the solution is to look at the so-called margin. It is the space around the splitting line and the closest points. And we see that in this case, this margin is small. But if we take this line, then the margin is maximal. So we want to maximize this margin. And we can describe the split line in terms of some vector W perpendicular to it, orthogonal to it, and then the split line is given by this equation. And the boundary line are given, boundary lines are given by this one and this one. So now the point belonging to the blue class should fulfill this inequality, and point belonging to the green class should fulfill this inequality. We can combine these inequalities into one inequality, and now our task is to maximize margin in subject to this inequality. It can be shown that the width of this margin is equal to over norm of W. So we need to minimize W in order to maximize margin. And then after finding optimal W and B, we can classify some new data just by computing sign of this expression where X is feature vector of this new point. And this task, which I show, is called, this case is called hard margin, because we don't allow any point to be in the margin, but it is more useful to try what is called soft margin, where it is possible for a point to be in the margin, but there is some penalty for doing this. And in the soft margin case, we need to modify our inequality by small parameter xi. And it can be shown that our problem can be reformulated in this way. Now we need to find some alphas such that first expression is minimal, and the second expression works as a constraint, where C is some constant that regulates how soft is our margin. And the third expression shows the classifier after finding optimal alphas. Okay, so this works quite well, but what about situation where the points cannot be separated in a linear way. If we look at this example, we can see that these points can be separated by a circle, but not by a straight line. And this is where the kernel trick comes to the rescue, because we can look at these points as a point in some higher dimensional space, for example, in 3D space. And now we can apply a transformation to these points. For example, this is transformation which gives third coordinates as a sum of squared coordinates x and y. And now we can see that that there is some flat surface, some straight hyperline, which separates these two classes of points. Okay, so let me formulate this kernel trick more precisely. So we have some original feature space of our data, for example, two-dimensional space, and then we apply some map phi to some higher dimensional space, for example, R3. And now this expression that we want to minimize changes a bit. Namely, we need to change the scalar product of two vectors in the original space to the scalar product of these vectors, of images of these vectors, the scalar product in this new larger space. And here we can make a fundamental observation for kernel tricks that we don't need explicit images of vectors, and we don't need explicit form of this map phi. We just need value of scalar product in higher dimensional space. So we can introduce some function k, which takes these two vectors and gives value of scalar product for some map phi. And we don't need to know this map explicitly. We just need some function k, which is positive semi-defined. And then we can compute the value of this function k between all pairs of points in the training set. And this is called the kernel matrix. Okay, so now we can move to the quantum kernels. So since in order to perform the kernel trick, we only need to map from the original feature space to some higher dimensional space, then we can use as this target space, we can use Hilbert space describing the quantum states of the qubits. In the case of our data, because we have 4 bands, it means each pixel is described by 4 values. We can make a map from 4-dimensional space to Hilbert space of qubits. In other words, we want to assign quantum states to different pixel values. So we can introduce some unitary operator u, which is parameterized by the feature vector x, these values of given pixel, and then the kernel function can be defined as the squared scalar product of quantum states representing 2 different points in dataset. And we can compute this value using, for example, the following circuit. First, we apply unitary operator associated with some point xi, then Hermitian conjugation of unitary operator associated with some other point xj, and then we perform measurement, and the probability of values 0 on all qubits is value of our kernel function. So the task is now to find some concrete form of this unitary operation U. We can take a look at the some building blocks for this task. So we need some layer of gates which encodes our data points into quantum register. So for example, here we call this S, and this S operation consists of Hadamard gates, which introduce some superpositions on qubits, and then we apply rotations around z-axis on the Bloch sphere, and these rotations are parameterized by values in our feature vectors. But we also need some layer of gates with some parameters. Then we can tune these parameters to find the best kernel. So we have some ansatz for our kernel, but in this ansatz we still have some freedom in some parameters to find the best one. For example, we can parameterize this kernel in this way. So we have some parameters theta, 12 parameters in this case, for example, and these parameters parameterized rotations around z and y axis of Bloch sphere. And also we can introduce some entangling layers, for example, this kind of circular control node gates. And then we can combine all of these layers. We can repeat these layers many times to find the best structure of this circuit for kernel. So, for example, here at the beginning we encode our data in qubits. Then we apply this parameterized part, then some entangling layer, then we can repeat this once again, and so on and so on. Okay, but how we can measure which kernel is better? So let's imagine ideal kernel. Ideal kernel should have following form. So ideal kernel should give 1 if data points are in the same class, and -1 if these data points are in different classes. So we can express this ideal kernel as an outer product of vectors of labels. Yeah, y are vectors of labels, so y this vector y is just vector of -1s and 1s as a labels. And now we want to somehow compare our kernel, which is parameterized by this parameters theta, and this ideal kernel. So to compare two matrices, we can use following formula. This is Frobenius product between matrices, and it is divided by Frobenius norm of these matrices to normalize this. And if we put here our ideal kernel and some our kernel k, then we have this expression. This is called target alignment. So here we see that we need to somehow tune this parameters theta to find the maximal value of this expression. So to find the kernel which is the closest kernel to the ideal one. Okay, so we need to maximize over theta. Okay, so this is something. Okay, And in our case, we train and test our model on data from Landsat 8 satellite. This is just map to show what areas of the Earth was photographed in the train and test sets. And these are some example pictures and some examples results. So we have this kind of pictures. These are pictures in the so-called false colors, because here we have 4 bands: blue, red, green, and infrared. So this infrared needs to be somehow represented on the picture. So these are not natural colors, but somehow mixed with infrared. And we see cloud. Here we see ground truth. So this is a picture where white pixels correspond to clouds and black pixels correspond to the pixels without clouds. And this is our train set. And here we have few examples of different kernels, classical ones and quantum ones, how it performs on these examples. So in these pictures, white color is true positive. So yeah, true positive results. Black pixels are true negative, blue false positive, and red false negative. And this is linear kernel. So this linear kernel is not very good. This is the simplest kernel, just normal product of feature vectors without any mapping to the higher dimensional space. Classical one. Here we see a RBF classical kernel, which works quite good. And here we see some quantum kernels, WS, WS, WS. These are just names corresponding to the structure of these layers of quantum gates, which I showed previously. So here are these results, some example results. Here we can see another picture with the different structure of clouds. Here we can see that these results are not quite good, because on this picture we have some very it is not very cloudy picture, and so this is very hard to recognize this shallow clouds. Okay, and some another example with some different structure of clouds. And here we can, this was just examples, and here we can see results of and comparison between different kernels, classical ones and quantum ones, after many training and testing stages. So the green one is classical linear. No, I'm sorry. The green one is a quantum kernel, but with just ESC layer. So this is just encoding of feature vectors and nothing else. So this is not good. And then we see other kernels. Orange one and blue one are classical kernels. Blue one is RBF kernel, and orange one is classical linear kernel. And red, purple, and brown are quantum kernels. So we see that our model and our quantum kernels can can be compared to the classical ones. But we don't see here any advantage of this. But we can see that this kernels, quantum kernels, are almost as good as classical one RBF, but are harder to optimize because classical kernel RBF has just one parameters, and in our quantum kernels we have many parameters, so it is harder to optimize. And interesting observation from this our experiment is also that in this case, in these kernels, we don't need entangling layer. Here we can see that entangling layer is this E layer. So this is in purple color on this plot. So we see that this purple plot is basically worse or equally good as brown or red, which are without entangling layer. So it is quite interesting. So this is just kind of hello world problem in remote sensing in satellite images analysis. But it is interesting to try things, these quantum kernels in not obvious areas. Okay, so thank you for your attention.
Okay, great. Thank you. Thanks, Grzegorz. All right. So as previously, if there are any questions to Grzegorz, please post your questions on the chat because now we are running out of time slowly and we have to go to our last session for today. Sebastian Zając give a workshop about Bayesian quantum algorithms.
Okay, so hello everyone. Thanks for invitation and thanks the organizers for inviting me to be with you. At the beginning, I want also thanks my colleagues to give us a very theoretical and very technical issue to and very technical information for what we can do with quantum machine learning fields. So I will maybe start my slides, but I will change it for something different. So at present, I will okay, maybe I will do it right.
Yeah, I can see your slides.
Okay, so it will be a short introduction to variational quantum algorithms. So as we saw and heard that probably a lot of things was said about this approach to the quantum algorithm, but let's say that we want to do something on the machine learning, machinery, and deep learning. So I suppose that you have more intuition in that field. So because I am maybe short introduction, I'm a physicist, but at present I work as a MLOps and I do more with machine learning models and deep learning models with not only tabular data, but also for graph data and other kinds of things. And if you are familiar with machine learning or deep learning, it doesn't matter. You probably know that we can derive and divide our tasks for traditional way in that we can do some kinds of classifications, some kinds of regression problems. If our prediction value are continuous, But of course, if we don't have a target in our data, we can do some kinds of segmentation, and we can divide our data for some groups or some similar segments. Of course, we can mix together these kinds of things and get better results. In my case, I will cut everything to the classification problem, even for easy thinking, it will be a binary classification problem. So it will be simplest case at to work. So when we spoke about machine learning kinds of thinking or computer programming for data analysis, we can, of course, we must have some training data, and we want to produce some model. Of course, this model contain information about our data, but also contain information about some parameters. And because we have labels, we want to produce functions that with some parameters on our data. And for new kinds of data, we want to predict correctly our labels. So traditionally, this machinery is connected more for me with numerical kinds of finding of these parameters. So we define some cast function. So this probably is better seen in deep learning machinery, but don't worry, even if you want to do everything by machine learning machinery, probably your computer programs do exactly the same procedure, that you define some cast function. Even if you don't see it, it works like that. And numerically, you update your parameters and you find your correct results. Of course, in some cases, this is an approximation solution, but sometimes we can find exactly solution, for example, for simple regression problems. So in our case, from other point of view, we know that we do our computation on our classical computers. I just give you one remarks that okay, our computers work, and we call it classical computers, and they work on the classical Boolean algebra and classical gates. But of course, they work because we have some quantum effects, and this is how transistor works. So here we have also a lot of physics, of quantum physics. So it is not that quantum physics is only here. But of course, at present, we can say that maybe better say we don't have quantum computers, but we have quantum processor, coprocessor, which we can put to our classical device and control this quantum computation, and and produce some results which we can transform to our problems. So how this kinds of quantum computer process looks like is for its traditional way. For every kinds of processing, we prepare some state on some Hilbert space, or maybe even some more investigated space, and we take some binary, some evolution. This is, of course, a kind of gate model, but in other cases, in other type of modeling, we can see some similarities. And after that, we take some measurement and produce our result in the classic world. So this is some level that we don't see exactly, but we just know how to prepare state and how to take measurement results. Okay, so in this two picture, we can ask, okay, can we replace our model in machine learning or in deep learning with quantum computation, which can be, of course, beneficial and gave us some supremacy or some advantages. Of course, it's not so easy, and at present, it's not so obvious that you can use quantum computer for everything and it solves your every problems, but of course we work on this. So as Paweł and my colleagues said, we can use something called variational quantum circuits, and the main idea is that how we can use these quantum processors, quantum computers, and how we simulate something like we train neural networks. This is, in my opinion, this is if you want to start with variational quantum circuits and understand how it works, the neural networks are the best classical analogy how we can how you can derive everything on this this pattern. You can find other names for variational quantum circuits like parametrized quantum circuit or even quantum neural networks. It's all connected with this this quantum gate model. So application, as we saw, for pictures, for many other kinds of classical machine learning or deep learning task. But of course, main application comes from chemistry, from optimization problems, for solving some equation, and of course, many others. So before I show you some theoretical aspects, let's go to the some computer programs. I will just show you maybe one things, because I think that it is better do some computation, and I will try maybe I will try give you some examples that a few examples that can show you how you can treat your quantum circuits or quantum computing for your machine learning process. And I will start, of course, from loading some data. It will be trivial iris data, because I don't want to go to the special cases or different kinds of data. It will be traditional tabular data with few columns. And because I want to get a binary classification, I will divide my data not for 3 classes, but for 2 classes. So it is the first 100 rows of data. I have our train table and our target table. I will do some min, max, scalar. This is a standard transformation of data for better computation on for better computation in the case of our classical optimization algorithms. But of course, it's not so important for us. Okay, so because I will do everything from scratch, I will take for faster computation, I will take just not 4, but 2 features. It doesn't matter what are their names. So I can run. This is, of course, a traditional Python environment with libraries, with Qiskit libraries. It will be some information for how to use this library. Okay, so we know that we have our input data and our result labels, and we know that we want to get an algorithm, or it doesn't matter how you call it, but we want to take some function that produce our iris tab flower, depending what kinds of data you put them. Of course, this is classification task because we have 2 distinguished groups, 2 distinguished targets. So this is a binary classification task for 2 possible prediction. Okay, so I think that the best place to start will be not complicated types of models, but something different, that we can quickly find some very easy model. It's classifier.guest. So we can randomly put results, and we can see that, okay, I put some other functions, but they are just a function that gave me this classifier for each element, and evaluate this classifier on this label. So as I suspect, I get accuracy about 38%. Of course, if I will run it more times, I will get different answer. So this is correct random classifier. And I can check the result of classification for my data. And as I suspect, if I run this more than once, in statistic, we know that more than 30 elements of experiment is enough. So you see that we have correct answer, that 50, there is really random classifier 50-50 for each class. And okay, so this is from machine learning side of view, but what we can do on quantum circuit. Okay, we can produce a simple quantum circuit with 1 qubits, and we can initialize it with state, with superposition state for each element. So code is very trivial. You produce quantum circuit, you object, and on this object you initialize your state, and you take some typically job and get some results. I just show you that this state is correct, and this is superposition of these two states, two basis states. So how can I use and think about my classifier in that way? Of course, I can do something like quantum random model. Of course, it's if we will run it on the true quantum computers, it's very easy because it's just for 1 qubits. So you can produce these kinds of quantum circuits and run it on the true quantum computer. And because I won't use my functions, I will get results. I will put everything for the one shots, and I will get results with these kinds of functionality. This gave me a correct answer, because results is something like this. So I take information and produce integer from these results. So you see, yes, this is also our random quantum model, our random quantum classifier. So you see it is also good as this traditional random number generator. So you see, you don't need a very huge and very intensive thinking about how to generate something from simple quantum circuit, because here we have perfect random, not pseudo-random generator for your classifier. Okay, so, but of course, what is the next step? The next step is that we can see that, okay, we can derive our state as a linear combination, but of course, the main thing is how we can parameterize this states and everything in our circuit, that we can construct something that it depends on the parameters. And this is how parameterized quantum circuits was born, that we can use our superposition with some parameters, not only for the same value of amplitudes. So what it gave us, what kinds of possibility we have? We have also we can prepare our state divided by some parameter theta. Of course, for some theta, we should get the same results. So I can run my new model, Quantum2, and check that this is, of course, take more computation, but of course it's gave me good results. So if I go further, I will build a classifier contain information about parameterized quantum circuit. But what I want to do is take the backend also for the elements of my parameters, and of course I should say something about my data state. So this is of course simply the same quantum classifier, but it has few things that we can see that this is kind of our model. Here we have some post-processing of our results, and here we have some initialization of our data. So this is some pre-processing that we must take to get better and better classifier. So I can produce it, and this is how it looks like. So shortly, back to the okay, maybe further. So as I said, we can see the 3 steps here: the pre-processing to prepare our state. This is kind of classical computation and can be done on classical computer. As my colleague said, it is just quantum, it is just embedding out, which we change our data to the Hilbert space. Here we have some ansatz it's also a parameterized quantum circuit. And of course, after our result, we must take some information, what we get from the measurement and how to interpret it for our computation. So we have some post-process in our case. Okay, so for quick introduction, in Qiskit, you can easily parameterize your gates by parameter objects, and you can get information about this object. You can also put a parameter vector, which is better for if you have more than one parameters. And of course, but of course, the main question is, how do we know what kinds of gates and what kind of how many parameters and what kinds of parameters, and even how many qubits we should use? Of course, we don't know this. This is the same as in a neural network. When you start with neural network, you don't know how many hidden layers take to get good results. Okay, so as I said, in the pre-processing, we can proceed our data and encode our classical data to some Hilbert space, to some vector states. We can choose basis encoding, amplitude encoding, and angel encoding, and more sophisticated encoding. But what is important is that there is no one way to do it perfectly. It depends on the case you want to compute. But we can analyze the information how to choose. It can be derived by expressibility and entangling capacity of our embedding. So you can do easily 2 quantum circuits for data embedding, that this is just 1 quantum gate and 2 quantum gates. And what is the difference? You can see on this easy code that you randomly put information, and for the first, you can set your data just on this line of states on this sphere block, and on the second one you can get more points. So you probably not see it, but this is of course not only perfect way, because it has also some bad things, but probably you feel that this kinds of processing could be better than this one, but of course it depends on the kinds of problem. And the second one is we can choose, we can find information in entanglement process that we can entangle our qubits. So, okay, 2 minutes. So you see that we can produce non-entanglement kinds of embeddings, and of course we can put information about entanglement. And in the case of Qiskit, everything was done by the Qiskit library. So you don't need precisely describe everything, but of course you can. But you can use kinds of Z feature map like this one, which this is for 3 parameters. It is good to know that you can choose how many times you can use your gates. But as you see, it's just a trivial case of embeddings. You can use zzmap, which is more complicated, but you see that it contains information about entanglement process of your data. And this is just other kinds of entanglement parameters, linear and fully entanglement. So you see that we have very, very different kinds of methodology to how to choose our embeddings. Of course, there is also a Pauli feature map, which you can also reproduce as easy feature map. The second part was model. So for model, I will not also say much more, that you have also prepared objects for that, and you can produce your ansatz in very, very simple way. So as you can see, you can derive many kinds of ansatz with many different kinds of parameters. And okay, so let's go to the short examples because it's after my time. So as you can see, I choose two features. So I will choose ZZ feature map and model with 2 local. This is very simple quantum circuit for our variational algorithm. And of course, I define some functionality that I put our data to this circuit. And there is one very interesting thing is that it is not only choose data preparation and ansatz, but also it is important how you choose interpretation of your results. So one of the simpler things is using by parity function. So you put your bit strings and you get some kinds of answer. If you are interested, you can find information here, but there are also other kinds of interpretation of results. But if I use this one, so I use parity bitstring interpretation of our result, and I must define some label, how to get label probability, and how to get some cost functions. This is traditional functionality way, so nothing special. And what is nice, you can easily put some more information for your optimizer log. You can prepare it, you can choose some optimizer, and you can put everything to run. So it will be 3 minutes. So just give me some time. I don't know how to, maybe I will do it this one. And I will back to the, so to reassume all things I do, was that we can compare traditional quantum circuit, which is preparing some state, put some unitary transformation and get some measurements. We can change it with some parameters exactly here and here, and of course, because we have some parameters, we must take expected value for our circuit. And so our thinking about machine learning or deep learning modeling, we can say that we change our model for something like this. So this is kinds of parameterized quantum circuit we put here. And of course, we must do something with how to encode our classical data, how to choose our model with some parameters, and how to measure the circuit with, so how to take information about not only about our results, but also about the parameters and what it means that we have these kinds of results. And after that, we can use a classical techniques with optimization to change our parameters. So a simple example is VQE, so kinds of more most popular. So circuit ansatz is unitary couplet, cluster, single and doublets. Once function is expectation value of molecular Hamiltonian, so the minimum of energy, and training processor is gradient descent using the parameter shift rule. Very famous, the same kinds of algorithm QAOA that you choose repeated time evolution for cost and mixer unitarist matrices. A cost function is just a value of expectation value of cost Hamiltonian. And of course, it's encoding a discrete optimization problems. And you can use different kinds of gradient descent optimizer for this task. And of course, this is very important to know about variational quantum algorithms and parameterized quantum circuit, because a lot of things which is connected with quantum in the name, you can find. This is just application of these kinds of algorithms. So if you see anything kinds of this, you can be sure that this is kinds of our variational quantum algorithms. So, okay. So at the end, back to our code. So, okay, 3 minutes should get some results. And this will be end of my talk. But I want to show you just one thing. So please give me 1 second, or maybe more than 1 second. Okay, because I don't want to stop you. Maybe a few, 5, 4, 3. Before it took just 3 minutes, so I suppose it should be enough, but it doesn't matter. I can stop it okay. And what is also important that in Qiskit you have also not only feature map, not only ansatz in easy way, you can combine it easy way, but you can also put some object called variational quantum classifier. You can simply put this information and get probably faster, maybe. Okay. And future is maybe faster way. Sorry for that. As always, if you show something, it will be not working, but okay. Okay, doesn't matter, okay, because I see that, okay, feature map, and that's, okay, so, because I stopped something, it's not correct results, but what I want to show you is that it is very easy produce these kinds of classifier on Qiskit because you have prepared objects for it. So where is the problem? The problem is that how to define your feature map and how you define your ansatz, what kinds of optimizer you should take. So you see you have a lot of hyper I can say hyperparameters for this task. So this is how, in my opinion, this kinds of algorithms looks like. So thank you very much for your attention, and I finished. Thanks.
Okay, great. Thank you, Sebastian. So actually, I think that we've even finished a bit earlier than expected, but that's good. Do we have some questions now? So now I'm not sure if the other speakers are still with us, but if there are some questions, we can try to answer. Yes, I see that Grzegorz and Karol are still with us as well. Or the questions to Sebastian, of course. Okay. I don't see questions now, so I think we can conclude and finish. So first of all, Sebastian, Karol, and Grzegorz, thanks for all the interesting talks, and I thank the participants for attending and also for discussions that we had on chat. This meeting was recorded, so we'll later publish the video recording on our YouTube channel, and we'll try to distribute it among the registered participants. And after the meeting, we'll also send you a feedback form, so we'll be happy to read your feedback. And yes, on my slides at the end, there were some links to the social media profiles or our YouTube channel. So if you watch the recording later, you can subscribe to stay up to date. So with this, I think we can finish. So thanks everyone once again. I will now stop. Oh, there is one question from Konstantinos. How errors affected the results? I'm not sure if so. I didn't present any results in my talk, but maybe Sebastian or Karol or Grzegorz would like to tell something about it.
I could start if you don't mind.
Sure.
Okay. Let me just start video. I will share my screen because I actually have some experimental data uploaded, so I think it would be good to show it. Okay. Okay, so this is experimental plot. Okay, so this is a variation of quantum circuit that is optimized. So we have basically we try to do quantum generative adversarial network. And what happens is with that errors that are on IBM Q Montreal, now it's, I think this processor is retired, but it already had some errors. We did use some error mitigation techniques, but it turned out that only some of them were useful. It actually prevents you from the error prevents you from, for example, from reaching fidelity equal to 1. We set up a problem to have fidelity of our state generation to be 1, but we could not physically get to 1. So this is one the effect of errors. The other effect is actually that our cost function does not go to 0. We expect it to be 0 for optimal case. It just oscillates around some minimal value. Okay, so it's a problem because sometimes you don't know if your learning process is correct or not. So what we do additionally, we generate this cloud that you have here. This cloud is actually by running simulations of the obtained by running simulations of experiments for many times, and we see, okay, so this is what we should actually expect. And if you finally, when we run an experiment on a real quantum processor, the points should be somewhere within this cloud. So from this, we can also estimate how many iterations or epochs for training we need to implement. So this is how this looks in practice, and errors are actually so large that this is just a very simple training problem for generating balanced superpositions of zeros and ones. So our generator is basically arbitrary 2-qubit unitary operation. There's also a discriminator in the same circuit, which discriminates between balanced superposition of 0 and 1 and something that is not a balanced superposition of 0 and 1. And so we train these two elements of our network, and the depth of the circuit is around 20 something. Okay, so this is like 20 something, 20 gates. So already the errors are quite substantial. And what you can do to basically to have some useful results at the end is to use like dynamical decoupling. So this is something that IBM actually made possible some time ago. It was quite a novelty a year ago, but now I think it's well known. So, but other methods are either have a huge computational overhead or like zero error extrapolation. They just miss the target completely. In our case, so we don't we abandoned using them. So this is how we do it. We actually perform simulations, try to do a dynamical decoupling, and then it actually you will not have a perfect result in the end, but something that is usable. Okay, so this number, like fidelity is something 98 or 99, it's quite good, because this is also what we have in our optical experiments. So if you have like a simple caged system that is very stable and the errors are really small, and you just have bulk optics and it's also very reliable, you will also have some errors. So usually we stop improving our setup when we reach fidelity about 99% or 98 point something percent, because then it's almost impossible to do this. It will take a lot of time. So always there is some we live in a perfect world, so we have some margin for error. So in other experiences is the same. I think we also have fidelity around like 98%. So this is what happens if you don't have like quantum error correction. So in perfect case, we also do some simulations just to without errors, just to see if in principle our approach would work. So this is how we deal with errors. We assume, for example, they don't exist, and we run computer simulations. This is the last resort if nothing else helps. Okay, so I think that this is it. Okay, so. I hope that I answered fully to your question. Let me just stop sharing.
Thank you, Karol. So unfortunately, Sebastian had to leave us because due to some other duties. But maybe Grzegorz would like to add something.
Yeah, I can add just that the results that I showed were obtained on classical simulator, so there were no noise. Yeah. So, but in general, of course, the noise is the problem.
Okay, good. So Sebastian just sent me a message that if someone would like to check the codes that he used, he can share the notebooks that he was presenting. So we'll try to do it. We'll try to just get his notebooks and share it with the registered participants. All right. Do we have other questions? Okay, so I think we can conclude our mini conference. So once again, thanks Karol and Grzegorz for participating and for great presentations and answering the questions. And thanks everyone for attending. So hope you enjoy it. We'll ask you for the feedback, and we'll later publish the video recording, hopefully. Thank you. Bye bye. Have a good weekend.
Thank you. Bye.